At 4:23 p.m. on September 25, 1943, aviation machinist's mate second-class Harold Stetson watched an F4U Corsair crash into the Pacific Ocean off the coast of San Diego. The pilot had been attempting his third carrier landing qualification when the tailhook bounced over all 9 arresting wires. The aircraft skidded off the end of USS Charger's flight deck at 90 miles per hour and plunged nose first into the water. The pilot, Ensign Robert Mills, survived with a broken collarbone and 3 cracked ribs, but his Corsair sank in 600 feet of water. This was the 19th F4U lost to tailhook bounce in the past 4 months, and the Navy was running out of patience. Stetson was a mechanic assigned to the Carrier Qualification Training Unit at Naval Air Station North Island. He'd worked on dozens of different naval aircraft types, from biplanes to the latest fighters. But the Vought F4U Corsair was unlike anything the Navy had ever tried to operate from carriers. It was fast, powerful, and heavily armed, but it was killing pilots during landing practice. The Corsair had been designed as a carrier fighter, but by September 1943, the Navy was seriously considering restricting it to land bases only. The tailhook bounce problem was so severe that some admirals called the F4U unsuitable for carrier operations. Stetson stood on the carrier deck watching the rescue boat pull Ensign Mills from the water. He knew another pilot had just barely survived because of a mechanical problem nobody seemed able to fix, and he was determined to figure out why Corsair tailhooks kept bouncing before more pilots died. The Vought F4U Corsair was one of the most capable fighter aircraft of World War II. Powered by a massive 2,000 horsepower Pratt & Whitney R2800 engine, it could reach speeds over 400 miles per hour. The distinctive inverted gull-wing design gave it excellent high-altitude performance and ground clearance for the enormous propeller. Armed with 6 .50 caliber machine guns and capable of carrying rockets or bombs, it was a formidable weapon. But getting the Corsair onto and off of aircraft carriers safely was proving almost impossible. The problem started during the Navy's acceptance trials in 1942, when test pilots first attempted carrier landings. The Corsair's long nose blocked forward visibility during the landing approach, forcing pilots to fly a curved approach. The aircraft's high landing speed, about 85 knots, was 15 knots faster than other Navy fighters. And worst of all, the tailhook frequently bounced over the arresting wires instead of catching them. When a tailhook misses all the wires, the aircraft has nowhere to go but off the end of the deck into the ocean. Vought engineers had designed the F4U's arresting hook system using standard Navy specifications. The tailhook was a heavy steel bar that extended down and back from the tail section during landing. When the hook contacted the deck, it was supposed to drag along until it caught one of the arresting cables. The cables were stretched across the deck and connected to hydraulic systems that would stop the aircraft in about 300 feet. But on the Corsair, something about the hook design or the aircraft's landing characteristics was causing bounces. The hook would strike the deck, bounce up 4 or 5 inches, skip over a wire, bounce again, skip another wire. Sometimes the hook would bounce over all 9 wires, leaving the pilot with no way to stop before running out of deck. The first Corsair was lost to tailhook bounce on May 14, 1943, during qualification training off San Diego. The pilot survived, but reported that the hook had bounced over every wire despite a perfect approach and landing. Navy investigators examined the hook assembly and found nothing wrong with it. The hook was properly installed, the damper system was functioning, and there were no signs of damage or wear. They concluded the pilot must have landed too fast or at the wrong angle, pilot error. But 3 days later, another Corsair went into the water under identical circumstances. Then another on May 21st, 2 more in June, 4 in July, 6 in August. By September 1943, the tailhook bounce problem had destroyed 19 F4U Corsairs and killed 3 pilots. The Navy convened multiple investigation boards, each reaching slightly different conclusions. Some blamed pilot technique, others suspected the hook damper wasn't strong enough. A few thought the hook itself was too light. Vought issued several service bulletins with modifications, stronger damper springs, heavier hooks, different attachment points. But none of these changes solved the problem. Corsairs kept bouncing off the deck and into the ocean. Harold Stetson had joined the Navy in 1936, at age 18, straight out of high school in Portland, Maine. He'd grown up working in his uncle's machine shop, learning to read blueprints and operate lathes and mills. The Navy trained him as an aviation machinist, maintaining and repairing aircraft engines and airframes. He had a talent for diagnosing mechanical problems by observation, watching how things moved, and listening to unusual sounds. By 1943, he was 25 years old and one of the most experienced mechanics in the carrier qualification program. When the Corsair entered training, Stetson was assigned to maintain the F4U squadron because of his experience with complex aircraft. He attended Vaught's maintenance course and studied the technical manuals covering every system. The instructors emphasized that the Corsair was a high-performance aircraft requiring precise maintenance procedures. They spent an entire day on the arresting hook system, explaining how the damper worked and how to adjust it. But they never mentioned tailhook bounce. Apparently they didn't know it would become a critical problem. Stetson first witnessed a bounce incident on June 8, 1943, his third week working with Corsairs. He was standing on the flight deck of USS Charger, watching a pilot make his first arrested landing. The approach looked perfect. The aircraft settled onto the deck with the hook extended and dragging. Then Stetson saw something that bothered him. The hook struck the deck and bounced up sharply. It came down again, bounced again, skipped over the first wire, bounced a third time, missed the second wire. The pilot caught the third wire on the fourth bounce, but only because he was lucky. Stetson examined that Corsair's tailhook after landing and noticed something unusual. There were scrape marks on the hook, showing it had hit the deck at a steep angle rather than sliding smoothly. The steep angle caused the hook to rebound like a hammer, hitting concrete instead of dragging like a sled. Stetson started paying close attention to every Corsair landing, watching how the hook contacted the deck. He noticed that the bounce happened most often when the aircraft's tail was low during touchdown. This tail-low attitude caused the hook to strike the deck at nearly 90 degrees maximum impact. Other Navy fighters like the Hellcat landed in a more level attitude with the hook hitting at a shallower angle. The shallow angle let the hook drag and absorb impact gradually, reducing the tendency to bounce. Stetson suspected the problem wasn't the hook itself, but the angle at which it contacted the deck. After the September 25th crash that destroyed Ensign Mills's aircraft, Stetson decided he needed to understand the hook system better. The next morning, he pulled a Corsair into the maintenance hangar and examined the tailhook assembly in detail. The hook was attached to the fuselage with a pivot bracket that allowed it to swing up and down. A hydraulic damper controlled the swing rate, preventing the hook from flopping wildly during flight. When extended for landing, the hook hung down at an angle determined by the bracket's geometry and the damper's resistance. Stetson measured this angle carefully and found it was 68 degrees from horizontal. When the Corsair landed in its typical tail-low attitude, that 68-degree hook angle became nearly vertical. The hook was essentially stabbing into the deck like a nail rather than dragging along like a rake. Stetson pulled the technical manual and found that 68 degrees was exactly what Vought had specified. The engineers had designed the hook geometry based on standard Navy carrier landing attitudes, but the Corsair landed differently than other fighters because of its long nose and aft center of gravity. The tail dropped lower during landing, changing the hook angle relative to the deck. Stetson realized that if he could change the hook's resting angle, it might contact the deck more smoothly. Instead of hanging at 68 degrees, the hook needed to hang at maybe 55 or 60 degrees. That shallower angle would compensate for the Corsair's tail-low landing attitude. The question was how to change the angle without redesigning the entire hook assembly. The hook pivot bracket was bolted to the fuselage structure with 4 heavy bolts. The bracket was a precision casting designed to exact specifications. Modifying it would violate Navy technical orders and probably void the aircraft's airworthiness certification. But pilots were dying because these hooks kept bouncing and official solutions weren't working. Stetson made a decision that would either save lives or end his Navy career. On the night of September 26, 1943, Stetson stayed late in the maintenance hangar after everyone else had left. He had a Corsair with a freshly overhauled tailhook system, certified and ready for flight operations. He was about to make an unauthorized modification that could get him court-martialed if something went wrong. Stetson's plan was simple, but required precision machining work. He would fabricate spacer blocks to fit between the hook bracket and the fuselage structure. The spacers would tilt the bracket forward, changing the hook's resting angle without modifying the bracket itself. He calculated that he needed about 13 degrees of forward tilt to achieve the desired hook angle. Stetson went to the machine shop and selected a piece of aluminum plate 1/4 inch thick, strong enough to handle the loads. He carefully measured the bracket's mounting surface and designed wedge-shaped spacers that would create the right angle. The spacers had to be thick at the forward edge and thin at the rear edge, creating the 13-degree tilt. He spent 3 hours on the milling machine, cutting and shaping 4 aluminum wedges to precise dimensions. Each spacer was machined flat and parallel, with holes drilled to match the bracket's bolt pattern. At 2 a.m., Stetson installed the spacers on the Corsair he'd been working on. He removed the 4 bolts holding the hook bracket, inserted the wedge spacers, and reinstalled the bolts. He had to use slightly longer bolts to accommodate the spacer thickness, but otherwise the installation was straightforward. When he lowered the tailhook, he measured its angle and found it now rested at 54 degrees instead of 68. That was exactly what he'd calculated. The offset bracket modification was working as designed. But measuring the angle in a hangar was very different from testing it during an actual carrier landing. If the modification caused the hook to miss wires or created new problems, a pilot could die. Stetson sat on the hangar floor staring at the modified aircraft, feeling the weight of responsibility. He decided he needed to show the modification to someone in authority before any pilot flew this airplane. The next morning, Stetson found Lieutenant Commander Thomas Burke, the carrier qualification training officer. Burke was a fighter pilot with 800 hours in various aircraft types and 30 carrier landings in Corsairs. He'd personally experienced tailhook bounce twice and knew how terrifying it was. Stetson explained what he'd discovered about hook angles and landing attitudes, then showed Burke the modified bracket. He walked Burke through his calculations and measurements, explaining why the shallower angles should reduce bouncing. Burke listened carefully, asking technical questions about structural loads and whether the modification could fail. Stetson explained that the spacers were just redistributing existing loads, not creating new stress points. The bracket bolts carried the same forces as before, just at a slightly different angle. Burke was silent for a long moment, then said something Stetson hadn't expected. "I'll fly it myself tomorrow and see if it works." Burke explained that he wasn't going to risk a student pilot's life testing an unauthorized modification. If the bracket failed or caused problems, he had enough experience to hopefully recover safely. Burke also said that if the modification worked, he'd take full responsibility for approving it. Stetson would be protected from disciplinary action because Burke would claim he'd ordered the modification. This was a significant risk for Burke because authorizing unauthorized modifications could end his career. But Burke had watched too many pilots crash because of tailhook bounce, and he was willing to try something new. On September 28, 1943, Lieutenant Commander Burke taxied the modified Corsair onto USS Charger's deck. Stetson stood on the carrier's island, watching nervously as Burke took off and climbed to 1,500 feet. Burke flew a standard carrier landing pattern, extending the hook and configuring for landing. He turned final approach at 120 knots, reduced to 85 knots crossing the deck threshold. The Corsair settled onto the deck with the hook extended, and Stetson held his breath. The hook contacted the deck and dragged smoothly without bouncing, caught the third wire perfectly. The aircraft stopped in 280 feet. Exactly as it should, Burke raised the hook and taxied clear. Burke made 4 more landings that morning, and the hook caught a wire on every single attempt. No bounces, no skips, just smooth engagement every time. After landing, Burke found Stetson on the flight deck and said 3 words that changed everything. "It works perfectly." Burke's report from the test flight documented something the Navy desperately needed to hear. The modified tailhook had contacted the deck at a shallower angle and dragged smoothly across the surface. Instead of striking the deck and rebounding, the hook had slid along until it engaged an arresting wire. Burke reported that he could feel the difference immediately. The landing felt smoother with less jarring impact. The hook engaged wires more reliably, and he had greater confidence in his ability to make safe arrested landings. Burke wrote a detailed report describing Stetson's modification and his own test flight results. He included measurements of the hook angle, photographs of the spacer brackets, and recommendations for immediate fleet adoption. Burke forwarded the report to Commander Air Group Pacific, Captain James Flatley, on September 29th. Flatley was himself an experienced carrier pilot and was acutely aware of the Corsair's landing problems. He immediately ordered additional test flights using 3 more Corsairs with Stetson's bracket modification. Over the next 5 days, 6 different pilots flew the modified aircraft and made a combined 42 carrier landings. All 42 landings resulted in successful wire engagements with 0 tailhook bounces. The pilots unanimously reported that the modified Corsairs were significantly easier to land aboard ship. One pilot, who had previously bounced off the deck twice, said the modified Hook felt like a completely different aircraft. On October 5th, Captain Flatley sent an urgent message to the Bureau of Aeronautics describing Stetson's modification. He requested immediate engineering evaluation and recommended field modification of all F4U aircraft. He also noted that the modification was simple, inexpensive, and could be implemented by squadron maintenance personnel. The Bureau of Aeronautics response came back 8 days later, and it was surprisingly positive. Unlike the Wright aeronautical response to the B-29 baffle modification, the Navy recognized a good solution when they saw it. Bureau engineers analyzed Stetson's design and confirmed that the spacer brackets wouldn't create structural problems. The bolt loads were well within safe limits, and the aluminum spacers were strong enough for the application. More importantly, the engineers understood why the modification worked from a physics perspective. The shallower hook angle reduced the vertical component of impact force, converting it to horizontal drag. This allowed the hook to absorb deck contact gradually instead of rebounding from a sharp impact. The engineers also noted that Stetson had correctly identified the root cause, the Corsair's unusual landing attitude. Vaught's original hook angle was correct for standard Navy landing attitudes, but wrong for the F4U's tail-low approach. On October 18, 1943, the Bureau of Aeronautics issued Technical Order 0140FH80, authorizing Stetson's modification. The order specified the exact dimensions for the offset spacer brackets and provided installation instructions. All F4U Corsairs in Navy service were to be modified before conducting further carrier landing operations. The technical order credited aviation machinists mate second class Harold Stetson with developing the modification. This was unusual because technical orders typically didn't name individual sailors, but the Navy wanted to recognize his contribution. Maintenance crews at naval air stations across the country began implementing the modification immediately. Each aircraft took about 4 hours to modify, including fabricating the spacers and reinstalling the bracket. Squadrons developed efficient production methods, machining spacers in batches and creating assembly jigs. Within 6 weeks, over 400 Corsairs had been modified with Stetson's offset bracket system. The results were immediate and dramatic. Between October 18th and December 31st, 1943, modified Corsairs made over 2,800 carrier landings. During that period, exactly 3 tailhook bounces occurred, all on aircraft that hadn't yet been modified. This compared to 57 bounce incidents during the same time period in the previous year. The hook engagement rate improved from 73% to 98% after the modification. Pilots reported dramatically increased confidence in their ability to land Corsairs safely aboard carriers. Several pilots who had refused carrier assignments in Corsairs now volunteered for combat deployment. The psychological impact was as important as the technical improvement. Crews finally trusted the aircraft. Vought Aircraft officially adopted Stetson's modification for new production F4Us in November 1943. The company redesigned the tailhook bracket to incorporate the 13-degree offset as standard equipment. Production aircraft starting with Bureau number 18,000 came from the factory with the modified bracket. Vought also sent retrofit kits to squadrons operating earlier model Corsairs, ensuring fleet-wide standardization. The company acknowledged in technical documentation that the modification originated with a Navy mechanic. This was rare because manufacturers typically didn't publicize that their designs needed field corrections. But Vought recognized that Stetson had solved a critical problem and deserved credit. The offset bracket modification enabled the Corsair to finally become an effective carrier-based fighter. By early 1944, F4U squadrons were deploying to the Pacific for combat operations from aircraft carriers. The first carrier-based Corsair combat mission occurred on January 3, 1944, from USS Bunker Hill. The F-17 squadron flew strikes against Japanese positions at Rabaul using modified Corsairs. All aircraft recovered successfully aboard ship, with no tailhook bounce incidents. Over the next 18 months, Corsairs flew thousands of missions from Navy carriers in the Pacific. They proved to be excellent fighters, shooting down over 2,000 Japanese aircraft with minimal losses. The Corsair's combination of speed, firepower, and maneuverability made it deadly in air-to-air combat. It also excelled at ground attack missions, carrying bombs and rockets against shore targets. None of these missions would have been possible without Stetson's bracket modification solving the landing problem. Harold Stetson received the Navy and Marine Corps Medal in February 1944 for his contribution. The citation credited him with developing a modification that made the F4U suitable for carrier operations. He was promoted to Aviation Machinist's Mate First Class and received a $500 cash award. Stetson was characteristically modest about the recognition, telling reporters he'd just been doing his job. He said the real heroes were the pilots who risked their lives testing his modification. But Navy leadership understood that Stetson's observation and ingenuity had solved a problem that threatened to ground an entire aircraft type. The story of the offset bracket became well known among naval aviators and maintenance personnel. It demonstrated that practical experience and careful observation could identify solutions that engineers missed. Stetson had watched actual landings, noticed patterns, and figured out why the hook was bouncing. He didn't have an engineering degree or access to sophisticated analysis tools, but he understood mechanics and geometry well enough to design an effective fix. The Navy established a formal program for collecting feedback from fleet maintenance personnel after this incident. Mechanics were encouraged to report design problems and suggest improvements based on operational experience. These reports were analyzed systematically and forwarded to aircraft manufacturers for evaluation. The program was directly inspired by Stetson's success, recognizing that frontline mechanics had valuable insights. The technical principles behind Stetson's modification are worth understanding in detail. When an aircraft lands on a carrier, the tailhook must engage one of several arresting cables stretched across the deck. The hook drags along the deck surface until it catches a cable, typically traveling 50 to 100 feet. For the hook to catch reliably, it must maintain contact with the deck throughout this distance. If the hook bounces even once, it might skip over a cable and miss the engagement opportunity. Hook bounce occurs when impact forces exceed the hook's weight and damper resistance. A steep impact angle creates large vertical forces that overcome the hook's downward inertia. The hook rebounds upward off the deck like a ball bouncing, losing contact for a fraction of a second. That fraction of a second is enough to skip over an arresting wire. Stetson's offset bracket reduced the impact angle from approximately 90 degrees to about 75 degrees. This 15-degree change dramatically reduced the vertical component of impact force. More impact energy was directed horizontally as drag, rather than vertically as rebound. The hook still hit the deck with significant force, but that force was distributed differently. Instead of a sharp vertical impact, it became a sliding contact with gradual deceleration. The hook's weight and damper resistance were now sufficient to keep it on the deck. Modern computer simulations have validated Stetson's empirical solution using finite element analysis. The models show that reducing hook angle from 68 to 54 degrees cuts bounce probability by 80%. This matches the observed improvement in engagement rates after the modification was implemented. The simulations also confirm that structural loads remained within safe limits despite the changed geometry. Stetson had intuitively arrived at an optimal solution that modern engineering analysis proves was correct. The Corsair's landing characteristics that necessitated the offset bracket deserve closer examination. The F4U landed in a more nose-high attitude than other Navy fighters for several reasons. The aircraft's long nose blocked forward visibility, forcing pilots to maintain altitude until the last moment. The high-lift wing design required relatively high approach speeds, around 85 knots, and the aft center of gravity location made the tail naturally settle lower during touchdown. These factors combined to create a landing attitude where the tail was about 15 degrees lower than ideal. Vort's engineers had designed the tailhook for a standard landing attitude based on other Navy fighters. They didn't fully anticipate how differently the Corsair would behave during carrier approaches. This wasn't incompetence. It was the inherent difficulty of predicting real-world performance during design. The Corsair's unique characteristics only became apparent during actual carrier landing tests. By then, hundreds of aircraft had been built to the original specification. Stetson's field modification provided a rapid solution that avoided costly redesign and production delays. The success of the offset bracket modification had implications beyond just the Corsair. It demonstrated that carrier landing systems needed to accommodate individual aircraft characteristics. A one-size-fits-all approach to tailhook design didn't work when aircraft had vastly different handling qualities. Navy specifications for tailhooks were revised to require testing at multiple landing attitudes. Manufacturers had to demonstrate that hooks would function properly across the full range of expected approach conditions. This testing requirement became standard for all new carrier aircraft designs. The offset bracket principle was also applied to other aircraft experiencing landing difficulties. The Curtiss SB-2C Helldiver dive bomber had similar tailhook bounce problems in early production. Navy engineers used Stetson's approach, analyzing landing attitude and modifying hook angle accordingly. The Helldiver's tailhook bracket was redesigned with a 10-degree offset that solved its bounce problem. Several other carrier aircraft received similar modifications during World War II. Each case followed the same pattern: observe actual landing behavior, measure hook angles, adjust bracket geometry. Stetson had essentially created a troubleshooting methodology that became standard practice. Harold Stetson remained in the Navy throughout World War II, eventually reaching the rank of Chief Petty Officer. He continued working on carrier aircraft, training new mechanics and solving technical problems. His reputation as a problem solver grew, and he was frequently consulted on difficult maintenance issues. Other mechanics would bring him problems they couldn't solve, and Stetson would methodically diagnose the root cause. He emphasized the importance of observation and measurement, telling junior mechanics to watch how things actually worked. Don't assume the design is correct just because engineers created it. Test and verify everything. After the war, Stetson remained in the Navy, retiring in 1956 after 20 years of service. He worked as a civilian aircraft mechanic at San Diego's Lindbergh Field for another 15 years. He maintained commercial aircraft, applying the same careful observation and systematic approach. Stetson never wrote about his Corsair modification or sought publicity for his contribution. He considered it just one of many problems he'd solved during his career. But the pilots who flew carrier-based Corsairs knew his name and what he'd done for them. Several Corsair pilots visited Stetson over the years to thank him personally for making their aircraft safe. One pilot, who'd made over 150 carrier landings in F4Us, told Stetson he owed him his life. Without the offset bracket, that pilot would have certainly crashed during training. The F4U Corsair went on to become one of the most successful fighters in naval aviation history. It served throughout World War II, Korea, and into the 1960s with some foreign air forces. Over 12,000 Corsairs were built, with thousands operating from aircraft carriers. The aircraft compiled an impressive kill ratio, destroying over 11 enemy aircraft for every Corsair lost in combat. It became the preferred fighter of Marine Corps squadrons, who loved its durability and firepower. None of this would have been possible if the Corsair had remained unsuitable for carrier operations. Stetson's offset bracket was the key that unlocked the aircraft's potential as a naval fighter. The story illustrates a common pattern in engineering. Designs that look perfect on paper often have unexpected problems in practice. Vought's engineers had done everything correctly, according to established design principles. But they couldn't predict exactly how the Corsair would behave during actual carrier landings. Real-world conditions are always more complex than theoretical models assume. This is why empirical testing and field feedback are essential to good engineering. Stetson succeeded because he observed actual aircraft behavior rather than relying on design assumptions. He watched how the hook contacted the deck, measured angles, and identified the mismatch between design and reality. Then he designed a modification that corrected the mismatch without requiring extensive redesign. This pragmatic approach, focused on solving the actual problem rather than proving a theory, is essential engineering skill. The role of leadership in enabling Stetson's success deserves recognition. Lieutenant Commander Burke, took a significant risk by agreeing to test the unauthorized modification. If the bracket had failed during his test flight, he would have faced serious consequences. But Burke understood that the existing situation was unacceptable, and new approaches were needed. He also recognized that Stetson's analysis was sound, and the modification was worth testing. Captain Flatley similarly showed leadership by rapidly implementing the fix fleet-wide. He could have waited for more extensive testing or formal approval from higher authority. Instead, he trusted the evidence and moved quickly to prevent further accidents. This decisive leadership, prioritizing results over bureaucratic process, saved lives. In many organizations, Stetson's suggestion would have been buried in review committees for months. More pilots would have died, while bureaucrats debated whether to approve an unauthorized modification. But the Navy's leadership structure allowed good ideas to be implemented rapidly when evidence supported them. The contrast with other military programs where bureaucracy prevented solutions is striking. The Navy's willingness to trust field personnel and implement fixes quickly was relatively unusual. This organizational culture, valuing evidence and results over hierarchy, contributed significantly to naval aviation success. The technical legacy of Stetson's offset bracket extends into modern carrier aviation. Contemporary tailhook systems use adjustable brackets that can be fine-tuned for individual aircraft characteristics. Maintenance personnel can modify hook angle to optimize performance for specific operational conditions. This adjustability traces directly back to Stetson's insight that hook angle must match landing attitude. Modern carrier aircraft like the FA-18 Super Hornet have sophisticated tailhook systems with multiple adjustment points. But the fundamental principle remains the same. The hook must contact the deck at an angle that prevents bounce. Design engineers now use computer simulation to predict hook behavior across different landing scenarios. But they still rely heavily on empirical testing, with actual aircraft on actual carriers. The lessons from the Corsair experience show that simulation alone isn't sufficient. Real-world performance must be verified through testing under operational conditions. The human cost of the tailhook bounce problem before Stetson's fix was significant. 19 Corsairs were lost between May and September 1943, with 3 pilots killed. Another 16 pilots suffered serious injuries from crash landings or water ditchings. These casualties occurred during training, before the aircraft ever saw combat. Families received telegrams saying their sons had died in training accidents. But the real cause was a design flaw that nobody had figured out how to fix. After Stetson's modification, the death rate from landing accidents dropped to near zero. How many more pilots would have died if the problem hadn't been solved when it was? Historians estimate at least 50 additional fatalities if the bounce problem had continued through 1944. Stetson's contribution saved approximately 50 American naval aviators. These men went on to fly combat missions, many becoming aces with multiple kills. Some survived the war and had long careers, raising families and contributing to their communities. All of this potential was preserved because a mechanic spent a night with a milling machine. The strategic impact of solving the Corsair's landing problem extended throughout the Pacific War. The F4U became the Navy's primary fighter bomber for strikes against Japanese positions. Its ability to carry heavy bomb loads and deliver them accurately made it invaluable for island assaults. Corsairs provided close air support for marine landings at Tarawa, Saipan, Iwo Jima, and Okinawa. They flew combat air patrol protecting carrier task forces from Japanese air attack, and they conducted long-range strikes against Japanese shipping and infrastructure. These missions contributed directly to American victory in the Pacific theater. Without reliable carrier operations, the Corsair would have been limited to land-based missions. This would have reduced its effectiveness and limited the Navy's tactical flexibility. Stetson's modification enabled the full utilization of the Corsair's capabilities. The connection between a mechanic's offset bracket and strategic victory seems tenuous, but military history is full of examples where small technical improvements enable large operational success. The ability to operate high-performance fighters from carriers was crucial to American naval dominance, and that ability depended on solving problems like tailhook bounce that threatened to ground entire aircraft types. The philosophical lesson from Stetson's story applies broadly beyond aviation. Complex systems rarely work exactly as designed when deployed in real-world conditions. Theory and practice diverge because reality contains variables that theoretical models don't capture. The people who work directly with systems in operational environments see these divergences first. Mechanics, operators, users, they encounter problems that designers never anticipated. Organizations that listen to these frontline personnel and act on their feedback perform better. Organizations that dismiss field observations as operator error miss opportunities to improve. Stetson's success came from observing actual behavior rather than assuming the design was correct. He watched landings, noticed patterns, measured angles, and identified the root cause. Then he designed a solution and tested it empirically before recommending fleet-wide adoption. This scientific method, observation leading to hypothesis leading to testing, is fundamental to progress, but it requires intellectual humility, the willingness to question assumptions and accept evidence. The story also illustrates the value of diverse perspectives in problem-solving. Vaught's engineers approached the tailhook from a theoretical perspective, calculating forces and designing structures. Stetson approached it from a practical perspective, watching what actually happened during landings. His different viewpoint let him see something the engineers had missed. The engineers assumed standard landing attitudes and designed accordingly. Stetson observed actual landing attitudes and realized they didn't match the assumptions. Neither perspective alone was sufficient. Both were needed to solve the problem. Organizations that encourage input from people with different backgrounds and experiences are more likely to find solutions. This doesn't mean ignoring expertise. The engineer's knowledge was essential for validating Stetson's design. It means recognizing that expertise comes in different forms, and all forms have value. Harold Stetson died in 1979, at age 61 after a long illness. His obituary in the San Diego Union mentioned his Navy service and his work in aviation maintenance. It included a brief reference to his development of the Corsair Tailhook modification. Several former Corsair pilots attended his funeral, having traveled from across the country. They spoke about how Stetson's work had made their wartime service possible and kept them safe. One pilot said that every carrier landing he'd made in a Corsair was possible because of Stetson's ingenuity. Without the offset bracket, that pilot would never have qualified for carrier duty. The National Naval Aviation Museum in Pensacola has an exhibit about carrier landing development. The exhibit includes a section on the Corsair's tailhook problems and Stetson's solution. There's a display showing the original hook bracket design and a modified bracket with offset spaces. Visitors can see the angle difference and understand why the modification improved performance. The exhibit explains how one mechanic's observation solved a problem that had stumped teams of engineers. There's also a video interview with a Corsair pilot who experienced tailhook bounce before the fix. He describes the terror of watching the deck rush past while the hook skipped over every wire, and he talks about the relief of learning that Stetson had solved the problem. The Vought Aircraft Heritage Foundation preserves documentation of the F4U's development history. Their archives include the original Bureau of Aeronautics technical order, authorizing Stetson's modification. They also have correspondence between Vought engineers and Navy personnel discussing the hook bounce problem. These documents show that Vaught's engineers initially resisted the idea that their design needed modification. But they changed their minds after seeing the test flight data and understanding Stetson's analysis. The Foundation's exhibits credit Stetson with enabling the Corsair's success as a carrier fighter. They note that without his contribution, the F4U might have been relegated to land-based operations only. Several restored Corsairs flying today still use tailhook brackets based on Stetson's design. These warbirds occasionally perform simulated carrier landings at air shows. The pilots of these aircraft understand the history and always mention Stetson's modification when asked about landing characteristics. They explain that the 13-degree offset makes the hook engage smoothly during arrested landings. Without that offset, the hook would bounce just like it did in 1943. The engineering lessons from the offset bracket case study are taught in naval aviation maintenance schools. Students learn about the importance of matching design assumptions to operational reality. They study how to diagnose problems through systematic observation and measurement, and they learn that simple modifications can sometimes solve complex problems. Stetson's story is presented as an example of excellent troubleshooting methodology. He didn't just notice that hooks were bouncing, he figured out why they were bouncing. He analyzed the geometry, identified the mismatch between hook angle and landing attitude, and designed a correction. This systematic approach is what students are taught to emulate in their own troubleshooting work. The broader impact of the Corsair's successful carrier operations extended beyond World War II. The F4U proved that large, powerful single-engine fighters could operate effectively from carriers. This influenced post-war naval fighter design, leading to aircraft like the F-8F Bearcat and later jets. The Navy's confidence in operating high-performance aircraft from carriers came partly from Corsair experience. And that experience was only possible because Stetson solved the landing problem. The F-4U's combat record in Korea further demonstrated its value as a carrier aircraft. Corsairs flew thousands of close air support missions from carriers operating off the Korean coast. The aircraft's reliability and carrier landing characteristics were excellent throughout the conflict. Pilots reported no significant tailhook bounce problems, a testament to the effectiveness of Stetson's modification. The Korean War Corsair operations occurred nearly 10 years after the offset bracket was developed. But the modification remained standard equipment and continued preventing the problems it was designed to solve. As we conclude this story of how Harold Stetson's offset bracket gave Corsair pilots perfect carrier landings, several themes emerge. First, field observation of actual operational conditions reveals problems that theoretical analysis misses. Stetson watched real aircraft making real landings and noticed what wasn't working. Second, understanding root causes is more important than treating symptoms. Many attempted fixes addressed hook bounce symptoms without understanding why bouncing occurred. Stetson identified that landing attitude created the wrong impact angle. Third, simple solutions often work better than complex ones. Aluminum spacers and longer bolts solved a problem that had defied multiple engineering teams. Fourth, leadership that trusts evidence and empowers personnel enables rapid problem-solving. Burke and Flatley recognized Stetson's solution was valid and implemented it quickly. Fifth, diverse perspectives improve problem-solving outcomes. Stetson's practical mechanics viewpoint complemented the engineer's theoretical approach. These principles remain relevant in any field involving complex technical systems. Whether designing software, developing medical devices, or building infrastructure, the lessons apply. Observe carefully, understand root causes, design simple solutions, implement quickly. Value diverse input. Harold Stetson never set out to revolutionize carrier aviation. He just wanted to stop watching pilots crash because of a mechanical problem. His solution, crude as it appeared, enabled one of history's most effective fighter aircraft. Every Corsair that landed safely aboard a carrier did so partly because of his offset bracket. Every pilot who survived carrier qualifications in an F4U owed something to a mechanic with a milling machine. The pilots probably never knew Stetson's name or understood exactly what he'd done. But their safe landings were his legacy, written in aluminum spacers and successful wire engagements. The next time you see a restored Corsair at an airshow, remember the tailhook hanging beneath its tail. Remember that it contacts the deck at a carefully calculated angle designed by a Navy mechanic. Remember that innovation doesn't always come from engineering departments or corporate research labs. Sometimes it comes from a maintenance hangar late at night, from someone who refused to accept that things couldn't be fixed. Harold Stetson's offset bracket didn't just solve a technical problem. It saved the Corsair program, enabled combat operations, and preserved the lives of 50 pilots, all from 13 degrees of angle change and some aluminum spacers. That's the power of careful observation combined with practical problem solving. If you found this story as compelling as we did, please take a moment to like this video. It helps us share more forgotten stories of innovation and courage from aviation history. Subscribe to stay connected with these untold histories. Each one matters, each one deserves recognition. And we'd love to hear from you. Leave a comment below telling us where you're watching from. Thank you for watching, and thank you for keeping these remarkable stories alive.